Okay, so what I'm going to do, guys, is I'm going to show you the VCAR table where they go through all the different spectrums. So one of the VCAR past exam questions, hi Matt, was name a spectroscopic technique, say what part of the spectrum it uses, and then how does it interact and what information will it provide. Okay, so this is a really important table for you guys to look at because it does provide a good summary. If we just have a look, AAS, do you remember what that's useful for analysing? Metals, very good. So AAS uses the visible part of the spectrum. It allows electrons to move from lower to higher shells. Do you remember? Higher energy shells. And then back down. So each part of the electromagnetic spectrum relies on this lower energy level to higher energy level. Okay? And do you remember what word we used to say, like to describe this gap? Quantized. What does that mean again?
It's from one to the other. There's nothing in
It's a set quantity.
A set quantity. That's what makes it so important for analysis, yeah? So for qualitative analysis, when we're trying to identify things, it's really important that we have that set gap, yeah? Like when we're doing the flame test and we look at one of potassium goes purple, it's because it's got these quantized gaps. Are you guys happy with that? Okay, so then we've got UV visible. Now let's focus on the two that we're looking at today. And that's infrared and hydrogen and carbon NMR. Okay, infrared looks at the infrared part of the spectrum and NMR looks at the radio waves, as you said. So let's do a bit of a revision of infrared. Infrared spectroscopy. Okay, who remembers how the infrared, well it says it on the board, but how it interacts with our substance? Yeah, it changes your vibration. Yeah? Do you guys remember the different vibrations it can have? You don't have to know, but remember we did the...
Remember scissoring.
And the whole stretching, twisting, out of plane rotations, blah, blah, blah. So basically, the important thing is, when we irradiate a sample with infrared radiation, it allows the molecule, they're always molecules. What's molecules again? Covalent bonding. So, covalent bonding, do you remember what we use as a cell? Like what we actually keep our sample in so that it doesn't interfere with the infrared, doesn't absorb any infrared?
It was an ionic compound, wasn't it?
It was an ionic.
Sodium something.
Yeah, so we can use sodium, we can use potassium chloride, sodium chloride even. Yeah.
What if it got dissolved? What if it's salt? Is it just literally a salt?
You don't have water there because the problem with water is it's a molecule and it can absorb.
Okay.
So our samples are not dissolved in water.
They're just solid.
Yes.
Oh,
Completely concentrated, just no water. They might be a liquid,
Yeah.
completely concentrated.
Yeah.
Okay, so importantly, the molecule might be vibrating with a low frequency over here. And then, if it absorbs infrared radiation corresponding exactly to this gap, it vibrates at a higher frequency here. So all you have to say is that infrared radiation, if it's absorbed, molecules vibrate at a higher frequency. Vibrate at a higher frequency. They move from low vibrational energy levels to high vibrational energy levels. Does that make sense? So this is really important to us because different bonds absorb different wavelengths in the infrared section of the spectrum. Yeah? So, do you guys remember what will absorb high energy?
Strong bonds.
Strong bonds, what do you mean by that?
Hydrogen
Sorry?
Hydrogen bonds.
No, it's actually the covalent bond that's absorbing, not an intermolecular bond.
Single bonds.
Do double or single bonds absorb higher energy?
Single bonds.
Double bonds. Double bonds, higher energy, and triple bonds than single bonds. Do you remember also the type of atom?
Wasn't the alcohols, weren't they? One with H's, whichever.
I'll give you an example. Say if we've got one to chlorine and one carbon to, let's do fluorine.
Electronegativity.
No, it's not to do with electronegativity, it's to do with atom size.
Oh.
Which one absorbs at a higher frequency? Which one moves around faster? F. Smaller. So smaller atoms tend to absorb at a higher energy and larger atoms tend to absorb at a lower energy. Okay? So, I think we've got that there. Okay, so infrared light, let's just see where it is on the spectrum. It's lower energy than visible light. So it's not enough energy to promote electronic transitions, but it's enough to change the vibration of a molecule. So longer wavelength, lower energy, not enough to excite electrons, but molecules can vibrate. So these vibrational energy levels are quantized, much like electron shells, yeah? But they actually respond to the amount of energy in the infrared section. The types of vibrations you don't have to know. I don't know why I put that there. I guess because it's cute. Remember when we did that?
Yes. Degrade.
Okay, so infrared spectroscopy. We've actually said all of this, so I'm not going to go through. I guess this last slide's important. So the triple bond is stronger, vibrates at a higher frequency than the double bonds, so they absorb at a higher energy. Okay, and the atom size really matters as well. So here we've got a chlorine attached, and it's 750 with a chlorine attached, but with a bromine attached, it's 600. Larger atom, smaller energy. Does that make sense? Now, you don't have to memorize those energies because where are they? Okay, they're all in your data book. The ones that you need to know are, I don't know, I guess how to identify them on a graph, okay? We have characteristic kind of troughs. Let's talk about what the graph looks like, okay? Do you remember what's on the x and the y axes of the graph? What do we measure the frequency in? It's not exactly wavelength. 1 over wavelength, yeah. So wavelength is this way. 1 over wavelength is that way. It's called wave number. Very good. Okay. Now, energy, which way will that go? In the opposite way to wavelength or in the same way? Okay. Energy goes this way and frequency goes this way. So in other words, this tells us something about... Matt, you done?
It's just funniness.
What is it?
Mr. versus Sunglasses case. Tweety bird.
Why do you have this? Oh, did you take a photo of it? Oh, okay. That's fine. Each to their own. Okay, so here we've got, it tells us something about energy. That's why when I was talking about those graphs before, or the tables before, we've actually got things with, I was saying that this was high energy. I actually meant it's high wave number, but it goes in the same direction. Yep.
Does it increase wave number? Decreases it goes away from the y-axis?
Okay, so in which way does it go? Yes. Higher wave numbers are over here. So it starts off at 0 and goes to like 4,000. It is backwards. So it says wave number, and the units for wave number, centimetres to the -1. Okay, so if we have a look at a few spectra, do you remember what alcohols?
Your wine glass.
Excellent, the wine glass. And you can see that spiky hand here. Do you remember what that is?
Chain, isn't it?
This is infrared. CH. So the CH, it's not a carbon chain. So these are looking at single bonds. Yeah? So this is infrared spectroscopy is good for functional group. Identification. Is this a qualitative or quantitative technique? Okay. Can it be used for quantitative analysis?
Not very well.
Yeah, it's not reliable at all. Okay, so we've got that. This is the CH bond, and this is the OH bond.
What's the y-axis?
So the y-axis is transmittance. So transmittance is sort of, think about it in the opposite way to absorbance. Think about it. You guys don't have to know about the ins and outs of the machine because it's been removed. But imagine that your sample's in here. You irradiate it with infrared energy. Sun passes through. That's called the transmitted light. Okay? So the transmitted light passes through. So the more light that passes through, the less it has absorbed. Yeah? So this shows you the absorbance. The less transmitters, the higher the absorbance. It's a backwards peak. It's called a trough. Yeah? Alright, so all alcohols should pretty much look the same. Now ketones, do you remember what ketones have? The groups.
Just a single bond, though.
Okay, no,
A double bond.
double bond, no. You just meant like that one bond. Yeah. Okay, so what wave number were they at roughly? 1,700. So it's around 1,700, whereas alcohols, the OH is around 3,300. It's in your data book. They've got two values. OH, alcohol, OH, acids. You have to be specific. So, which one is the C double bond O?
Is it that really lowest one?
Okay, so you get a nice, very thin, deep peak. Okay? So, unlike the OH, which is broad, carboxylic acids, what will they look like?
Like the alcohol gets closer to the CH.
Okay, it's not closer to the CH, it's actually a broader peak. Yeah? It's actually a larger peak. Sorry? Yes. So sometimes you can't actually see that the CH very well. Okay, so like for example here, you've got that, but notice we also have the C double bond O, which tells us about the carboxylic acid. Is this coming back? Yeah? Okay, so then we look at another one, esters. What do esters have? C to a single bond O and C double bond O. Esters the muscles, remember? Yeah? Matt, you liked organics? Come on. You remember what the ester group looks like?
Yeah.
Okay. Alright, so we should have a C single bond O. Now, can anyone tell me where that is?
The one in between those two.
Yeah.
This one. Okay, Eleanor, do you have your data book in front of you? Is that what you were reading off before?
No, my notes.
Oh, can you tell me what wave number the C single bond O is at?
1,000 to 1,300.
1,000 to 1,300. Okay, so beautiful. This is at 1,250. Yep.
So in the data book, what are the values in transmittance per wave number or?
No, just wave number. Transmittance is what's on the y-axis. Don't get confused because the x-axis is wave number.
Sorry, yeah.
Yeah. Okay. What else should have a C single bond to O? OH? Is that what you...
Ketone?
Oh, ketones. No. Ketones don't have a C single bond to O. They only have a C double bond to O. The acids with the alcohol. Let's actually see that if it comes out. Do that? Oh. That comes out really well. Well, remember that they're actual spectra, but VCAR draws all of yours to make it nice and easy for you. Okay, then we've got the fingerprint region. Do you guys remember what that is?
Yeah, region where nothing happens.
Not nothing happens, a lot happens there.
Too much happens.
So do you remember what it's due to? Do you remember where it starts? 1,000 or 1,500, so around there. This is technically like sort of part of the fingerprint region. It's a vague thing, but 1,000 centimetres to the -1 is called the fingerprint region. And what is it caused by?
Some other balls in the finger.
Rotations of the whole molecule. Okay? It's caused by rotations of the whole molecule.
Is there a gang fight on outside?
Yeah, Korea's getting pissed.
Is he having not pissed?
I thought you meant pissed, not angry.
Oh,
And I was like, in school, but no, then I realised.
Shut up! We're trying to learn.
God, we're the biggest nerds, aren't we?
Those dance ball kids.
I know, being all athletic. Alright, so you happy with that, guys? Don't look there. So basically, before 1,000, so after 1,000, or however you want to look at it, it is good for, so infrared spectrum above 1,000 is used to identify functional groups. So you happy with that? But below 1,000 is specific to the compound. So what could we use the fingerprint region for? Sorry, distinguishing between what? Two molecules, yeah. So say if you've got, you know that it has an OH only, I mean, how many possibilities are there? It could be methanol, ethanol, etc. You could do other techniques like mass spec, and that could clearly identify it, or you could use the fingerprint region. What do you mean? Oh, so you have to have a database to compare it to. Yeah, there's no way you can determine it just based on the fingerprint region. So you'd chuck it through a database and it would find a match for you. Okay, now let's look at NMR. That's actually all there is to infrared, okay? Nice and quick. NMR is, I don't know, I love NMR. But anyway, let's not listen to me. Huh?
Oh, the singlets.
I do, but NMR's special in a way. Remember, organic chemist goes home if it's broken? No? Alright, so NMR, what does that talk about? It uses radio waves, but what for? Let's step back.
Orientation.
Yes, orientation of what?
The poles.
Yes.
Poles of it.
And then, okay, so basically we have without an external magnetic field, and with, there's two possibilities. Okay, so what is it used for? What's NMR used for? Hydrogen environments, yep. So identifying hydrogen environments and ultimately,
Identifying like
so is it qualitative or quantitative?
it's qualitative.
Okay, so without an external magnetic field, let's just talk about proton NMR. You can have carbon NMR. Why do we need to use carbon 13 and not 12? Excellent. So this one has a spin state, and only because it has an odd number of either protons or neutrons. For example, nitrogen 14, how many protons does it have? Neutrons? It still has a spin because it has an odd number of either proton or neutron. What happens is your protons pair up, your neutrons pair up, and then you'll have a proton and a neutron left over, giving it the spin. Okay? So that's sort of like a little bit advanced. They have asked it once in VCA, and the answer was because it has a spin. Okay. So without an external magnetic field, they are all randomly orientated. Do you remember that? So this could be the north, where the arrow is. It is, actually. All randomly orientated. And remember that they're all at the same energy. Why are they all at the same energy without an external magnetic field? Why does it not matter how they're orientated?
Would they be orientated? Oh, pardon. Would they be orientated? Is this assuming like they're not even like on the Earth? The Earth isn't even like an external.
Oh,
Like,
they're not influenced by an external magnetic field. Yes. Okay. They pretty much, it's like a massive barrier inside. So, yeah, I know what you mean. They don't align with the Earth. Just assume no external magnetic field. So if they don't have an external magnetic field, they are not aligning with or against.
so those are atoms that.
Yes, they're protons. So
Those are
the
protons.
nucleus has a spin, but H, if it loses its electron, it's called a proton. It only has one proton in the nucleus. Does it have any neutrons? No. So that's why we call it a proton. And its nucleus, which is only made up of one proton, will spin in any direction without the application of an external magnetic field.
So is this only in hydrogen NMR? So in carbon NMR, would we call them atoms or?
The nucleus, it's still a nucleus inside the atom that spins.
Okay.
Yeah, yeah. So this is talking about nuclear spin. Good question. So nuclear spin. Then when we introduce an external magnetic field, what happens is this might be the direction of the external magnetic field. Do you remember if it wants to align with or against? With, definitely with. Your magnet points north to north, yeah? So, which one will it be at higher energy, with or against? Against, very good. So, when we apply an external magnetic field called HO, external magnetic field, you don't have to know that, but it's a subscript though. Okay, so external magnetic field, we have things which align with lower energy state and against higher energy state. We create that gap. Yeah? So that gap wasn't there, it's created by the external magnetic field. You can imagine that the gap will change depending on how strong your external magnetic field is. The stronger it is, the larger the gap. Does that make sense? Christina, you look a bit confused.
Yeah, so what does the gap refer to? The gap is the gap in energy?
Yeah.
So the stronger
Between
magnetic
align
field
with and against.
Oh yeah, so the stronger the magnetic field is, the smaller the gap would be, wouldn't it?
No. The stronger the so the gap is talking about basically how hard it is to go against the field.
Would it be
Okay.
super easy if it was a really strong field though?
If it was a really strong field, it would be very hard to align against. You'd have to be in a very high energy, unstable state to align against. Does that make sense?
Yeah.
Now, the point is we need to be able to get a homogeneous magnetic field. Do you remember what that means, homogeneous? Same all the way throughout the sample, because if we're changing this gap size throughout the sample, it won't be good for identification, okay? Identification, it's really important. These values pretty much are a reflection on the gap size. Okay, so we've got that here. So we're using radio waves. We'll just get up to that part. So randomly orientated without an external magnetic field, all at the same energy state. Then when we apply magnetic field, they align with or against, and we create those that are aligning against the field, a higher energy. Importantly, this energy gap that we have created is quantized. Very good for identification. Does that make sense? Okay, so these values are quantized values. That's why we can use them to identify. Sometimes they're a range. Why do you think there might be a range sometimes? Why they not, if they're quantized, why doesn't every hydrogen that's in this particular environment bond with, give us that exact gap? Yes, Christine?
Is it because of other things in the environment?
Exactly. So other things in the environment, neighbouring atoms and things like that might affect it, okay? Okay, so now let's talk about where we bring in radio waves. Do you guys remember where we bring in radio waves?
Is that what we
We use it for what?
Don't we try to get them to go against the external magnetic field?
That's exactly what we do, okay? So, we radiate it with radio wave radiation, radio wave, okay? It allows it to flip against the field, and then it's unstable. As soon as we remove the external magnetic field, it comes back down, and it emits everything that was previously, what's that word when it takes in energy? Absorbs. Okay? Okay, so we have those two states, blah, 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 just said that. Okay, so it takes in energy, flips against the field, unhappy, and then it goes back down and it releases the energy. Are you guys happy with that? Okay, now one thing we need to talk about is shielding. Do you guys remember what shielding is?
electron shielding?
Okay.
Isn't that making it easier to flip?
Makes it easier to flip. Yes, very good. The more shielding, the easier it is to flip. Matt, what are you doing?
Collecting pens.
Oh,
I mean, you got a lot of colours there.
I know. Look at this. I think I'm going to buy
I
a full
only got
pack.
one in this.
Sorry?
I only got one. I only got blue.
Oh. Poor thing.
Question,
Yep.
how do they actually measure the energy that they get back? Because they zap it with whatever, radio waves, yeah, and then they all flip.
And then they can, so a detector will be there, which detects the emitted light.
So they absorb it,
Yeah.
and then when they turn it off,
it's all instantaneous. And then as soon as they go up and then they come back down, they emit the light. Then the detector records
so
this
sort of
emitted frequency.
Going up and down.
It happens all instantaneous. Yeah, it's very, very quick.
Oh,
And as soon as they emit, the detector just detects the frequency based on the energy.
Yeah.
Yeah. Okay, so nuclear shielding, we said that electrons are spinning charged particles. And what do spinning charged particles have?
A magnetic field.
A magnetic field. So they generate their own tiny magnetic field. But the more electrons around, the more shielding you're going to have. So let's compare two bonds, an OH bond and a CH bond. I'll actually write them the same. Okay, let's talk about the shielding of electrons to this H. We're looking at proton NMR. Which one would be experiencing more shielding? This H or this H? More shielding?
The second one.
Second one. What does the oxygen do?
Let's suck the H towards it.
Doesn't suck the H towards it. No. Oxygen's, yeah. Oxygen's electronegative, sorry. So the electrons are pulled towards it, whereas this H and C are roughly similar. Okay? So this one has more shielding. So is it easier for this H to flip or for this H to flip? So easier. What's the value of a CH? What's the value of a methyl group in our data book? Let's have a look. A methyl group has a shift of 1. Whereas, so this has a shift of 1, that might be part of a methyl group. And the OH has 6, 1 to 6, so somewhere in between there. So as you can see, as demonstrated by that, the less shielding you have, higher chemical shift. That's the name of it. The chemical shift really refers to the gap between low and high energy levels. Okay? Now let's talk about C double bond OOH. This H, do you think it would be higher or lower? Higher. So it is. It's about 12. Okay? So we do see this effect. But lucky for you guys, you don't have to memorize them. They're all in your data book. Okay. So let's now talk about two last things, and then we'll just do a question. So, high resolution and low resolution NMR. Do you guys remember the difference between high and low resolution?
Peak splitting.
Excellent. Peak splitting. Okay, so for high resolution, actually going to draw this out as a picture. We're going to do, we're going to look at this molecule. Okay, so what's that molecule called again? Propanol, very good. Okay, so we've got propanol there. Low resolution first. What do the number of peaks talk about again? Number of peaks. Number of hydrogen environments. We're looking at hydrogen NMR. So number of H environments. Now, how many H environments does this one have? 4. So we have 1 here, 2, 3, 4. Why are these not part of the same environment?
They're affected by the neighbouring.
Excellent. So they'll have slightly different values. Now you can kind of predict where they're going to be. So the chemical shift, remember what the units for chemical shift are.
Something weird, like moles per ppm.
ppm. Okay.
Thanks.
Doesn't have much of it. No problem. See ya. Okay, so which one do you think is going to be furthest this way, like the higher values? We'll put a 12 here and a 0 here. That one or that one? This one? Very good. So 1 should be about here. Okay. Who remembers what peak height tells us?
Ratio of
Sorry?
Ratio
Ratio
of
of H's, very good. It's also called integration, and it tells us about the relative number of H's in each of those environments. Okay, so 1 should be there. Then if we do this one, it should be double as tall. So 2. So that one would be that. And then 3 should be the same height. Are you happy with that? And then I'm going to go off the chart. So, and then this one should be,
yeah.
and that's still, that should be 3. 4. That should be 4. What am I doing? Sorry? Oh, this is 0. Yeah. Okay. Do you remember what's at 0? TMS. So TMS, remember it's tetramethylsaline. It has all of these. Why do you think it has such a low chemical shift? Lots of shielding. So silicon, carbon, and hydrogen, all similar electronegativities, lots of shielding. Why only 1 peak? Only 1. Excellent. Total symmetry. So only 1 hydrogen environment.
What's it called again?
TMS, tetramethylsaline. Tetramethyl, 4 methyls. Okay, so are you guys happy with that? What was I going to say?
So why do we use?
Why do we use it? That's exactly what I was going to say. Why do we use TMS?
To make sure the whole thing is
To calibrate it, yeah. We want to make sure, so think about it. That gap is controlled by your magnet strength, your external magnetic field strength. So you can imagine that from machine to machine, you're going to have different strengths. Yeah, different strength magnets. It's going to be very hard to get the exact same strength. So to standardize it, because each machine is different, every machine has to calibrate it with TMS and give it a value of 0, so that these gaps stay the same between machines.
Why TMS in particular?
Because it's got a high shielding and it will be really far away from anything else. Very low shift. Okay, so high resolution, peak splitting. Let's have a look at each peak and see if it would split. Would this peak split? Tim, would that peak split? The
Yes. Is it about how many neighbouring relations?
okay, so sorry, n plus 1. Okay, so it's n plus 1. That's the rule. But what does the n refer to?
Is it directly neighbouring, like that has no neighbours?
Yeah. N refers to the number of hydrogens bonded to the neighbouring carbon atom. There's no neighbouring carbon atom. The number of hydrogens bonded to the neighbouring carbon atom, it's bonded straight to an oxygen, not to a carbon. Okay? It has to be the number of hydrogens bonded to the next door carbon. There's no next door carbon here. So number of H bonded to next door carbon plus 1. Okay, so that one's not split, and oxygen acts as a big fat blocker. Now, number 2, is this one split?
Yeah.
How many?
3.
1, 2, 3. Very good. 1, 2, neighbouring hydrogens, plus 1 is 3. Now, what happens to this peak size? It shrinks. You actually chop it into parts, okay? And it follows that probability, Pascal's triangle, wasn't it? 1, 2, 3, but it still has an integration of 2. Notice that it almost looks like 1 now. Should actually even be smaller. I'm pretty bad at that. Okay? So it still has an integration of 2. There's no way for you guys to know that. VCAR tells you at the top like that. Okay, then we've got this one. How many is this one split into? Or this environment with these 2 hydrogens?
6.
6. 1, 2, 3, 4, 5 plus 1 is 6. So that would look like very small. So 1, 2, 3, 4, 5, 6. But it's still got an integration of 2. Okay, so this is number 3. The integration is still 1, 2, 2. Okay. And then this one, is that split?
Yes. Split into 3.
3. Okay. So then it will be a bit taller. 1, 2, 3. And it's still group number 4, but it's got an integration of 4.
So, how do the ratios work? The integration, sorry?
They're talking about the relative number of hydrogens in that group.
So 3 out of a total of 8.
No. So this integration talks about how many hydrogens, the relative number in that group. So in this group, there's only 1 hydrogen. It's here. In this group, there are 2 hydrogens. In this group, there are 2.
Yeah.
And in this group, there are 3. What am I doing? Because I'm labelling it number 4. I'm getting confused now. Sorry about that.
But then 1, 2, 3, 4 is just numbers.
It's just, because I labelled this 1, 2, 3, 4.
Yeah.
Yeah. Does that make sense now? Okay. So let's look at an example. There's the shielding chemical shifts. Okay. So what I was going to do you guys want to take a trial exam now? It's the new trial exam for 2014 from STAV. And it's got one of these questions on it.
Cool.
Did you want to do that?
Yeah.
Or the CSE? Not sure which one. Maybe we should do CSE.